Hi everyone, welcome to our probability and analysis webinar. It's my great pleasure to introduce James Melbourne from CIMAD, who's going to tell us about reversals of Lyapunov's inequality. James, please.
Well, it's a pleasure to be here as much as we are here. A big thank you to Tomasz for the invitation and essentially for the project, because this work that I will talk about grew out of conversations with Tomasz and others that I'll mention as we go. But that said, this is a joint work with my unofficial student, Gerardo Palafox Castillo. He's at the University of Nuevo León in Monterrey. So here we go. So I'll give some definitions and some background on how I got interested in the particular problem that we'll talk about and why I think it's interesting. After that, we'll state a conjecture that Tomasz and I kind of decided might be true, as well as I think Tomasz's student Havrilla. And then Gerardo and I had a little bit of success with our investigations, we think, and I'll share those with you. And then we'll talk about some consequences of the inequalities derived. So, starting with Lyapunov's inequality, when we refer to Lyapunov's inequality here, what we're talking about is the log convexity of the LP norm, crudely speaking. And so this function, capital phi, is log convex. And by log convex, I just mean that if I take a logarithm of phi, then this function is a convex function in the usual sense. And this is for p greater than 0, if I'm not mistaken. And this is an immediate consequence of Holder's inequality. And I'm writing Holder's inequality in a funny way, but for me, it gives, I think it's nice intuition for why Lyapunov's inequality should be weaker. If we think of Holder's inequality, a funny way to write it down is as a function, hopefully I got everything right here, but as a function, and not thinking carefully like a good analyst, but just thinking about this crudely, algebraically as a function of potentials. If I plug in a v here, we have a function of some function space, and Holder's inequality can be stated as this. This map psi being log convex. And so in this sense, if we write things down like this, then you can do the computations and you can start with Holder's inequality and you can derive Lyapunov's inequality. But from this perspective, Holder's inequality should deliver a Lyapunov type inequality, because we're talking about the convexity of some function and of a vector space, whereas here we're just sliding along a particular point. If I write f is equal to e to the v. So this is like as you traverse a convex function in a particular direction, you get Lyapunov's inequality. And so I think I wrote reversals of Lyapunov's inequality, and we'll be interested in reversals in a discrete setting. Where things tend to be a little harder to come by. But in the continuous setting, these reversals are well known and classical. Going back to Borel in 74, this is in Rn, as I have it stated, and back to J.H.E. Cohn in 69, and this is just on in Euclidean space. And we can state that as the following for a concave function on some omega. Let's say that this is compact. So some compact, let's say a compact body. So we have some open interior. I don't want to do anything too exciting. Then the following function is log-concave. And it's in this sense that Lyapunov is telling us that these LP norms are log convex, and here we have some sort of reversal. If we multiply by some concave function, we're able to get log concavity, and so this constrains the LP norms behavior to be close-ish to linear, and we can formally generalize this. If we consider a function f to be S concave, and I'll only need S greater than 0 for now, if the following holds, and this is for X and Y in Rn and T between 0 and 1. So this is going to make us some power of a concave function. Then we can write this guy, we can formally generalize this to be for Fs concave with an S here, we're log concave. And if you take the limit as S goes to 0 of this formal improvement, then the same proof mechanics go through, and we have this limiting case, which will be especially interesting to us. And this is, we're still integrating. There's generalizations to log concave measures here, and not just the Euclidean measure. You'll have to adjust the power of n. The n that is appearing in the power, if I'm not mistaken, is an artifact of the Brun-Minkowski inequality, which guarantees us that the Lebesgue measure that I have here is 1 over n concave as a measure. But if that's unfamiliar to you, you'll lose nothing from the talk, because we're just going to be talking in a discrete setting, much less fancy, much more simple. But if it is familiar, I just wanted to mention it. So very good. So we have a reversal of Lyapunov's inequality. And there's a famous reversal of this is a famous reversal of Holder, known as the Procopaliner inequality. And so this can be understood as a functional generalization of the aforementioned Brun-Minkowski inequality. But this is just for setting. This is just props and background to try and establish some context. But it says if you take like the maybe we call this the supremum convolution. We have some convolution form. Another simple way to write this is if we have h of z that is larger than this quantity over here, any function that's larger will satisfy the integral of h of z larger. And so we have some sort of reversal of Holder in the sense that we have two functions and we have some combination of the functions whose integral will outdo the geometric mean of the two functions. Another way to write down Holder's inequality is to write it like this. And so Holder's gives us this little combination of the two functions has an integral that's smaller than the geometric mean of the two integrals, and Procopaliner gives us an upper bound. It gives us reversals of kind of holder type inequalities. And I'll just mention as an advertisement, if I take F and G, well, then there's some background for Procopaliner. This delivers the Brun-Minkowski inequality from convex geometry, which delivers things like the isoparametric inequality for Euclidean space. It also, Procopaliner guarantees us that marginals of log-concave functions remain log-concave. We also get all kinds of functional inequalities from Procopaliner type inequalities. One that I've always liked is a reversal of Renyi entropy comparisons. We also get things more conventional like the Gaussian log-Sobolev inequality. So you get like concentration of measure for strongly log-concave densities, and more generally in this same vein, the HWI inequalities from optimal transport. Provide another example. And the Procopaliner type inequalities are equivalent to, for Riemannian manifolds, to lower bounds on the Ricci curvature of a manifold. And there's beautiful generalizations of this stuff that, again, I'm just going to be keeping it real basic in just a moment, but just to give more context. And so one thing I'll mention is just like the Lyapunov inequality that we talked about up above can be derived from holder. We can derive from our reverse holder, Procopaliner, we can get our reverse Lyapunov. Procopaliner inequality wasn't so well known when Borel was proving his inequality, so it's not as easy of a trip back in 74, but now with our modern machinery that those folks provided us, we can give a very quick proof of that Procopaliner does improve the reverse Lyapunov. And by the reverse Lyapunov, I just want to talk about, and what I will hold on to is this statement, that if I have a log-concave density function, so this is f looking like e to the negative v for v convex, then this auxiliary function is log-concave. And the proof is amazingly simple. I couldn't resist including it for you. So what you do is we're claiming that this thing, this object is log-concave. That's what we wish to prove. We do a change of variables. I set, maybe I set u over p is equal to x. If I do that substitution, we get this equality. And then well-known fact, if v is a convex function, I think this is called the perspective function. This is jointly convex in P for P greater than 0 and X belonging to Rn. So I have V that's convex, then this perspective function is also convex. Just play with the algebra and it falls into your lap. I wish I had better geometric intuition for it. I believe that there is a geometric intuition to it, but it'll just come to you algebraically very easily. And then what we said is that Procopaliner says that the marginals of a log-concave function are log-concave. And log-concave functions are nothing but functions that can be written with a convex potential. And what we just showed is that this is convex. We're integrating over one of the variables. And that tells you that we're looking at this function is the marginal of a log-concave function. And boom, we have that reverse Lyapunov inequality. And so I just wanted to mention before I jump into things that there's been all kinds of cool work done on deriving or creating discrete Procopaliner, discrete Brun-Minkowski type inequalities that include going back at least to Olivier Villani in 2012, Goslan, Roberto, Sampson, Betali, Halikias, Klartag, and Slomka, and Slomka recently have some really nice, cool results related to a discrete Procopaliner. And I'll just mention that things are more delicate in the discrete setting. So the problem that I want to tackle is and I guess I probably should have mentioned it earlier, but what I'm aiming for is a discrete reverse Lyapunov. That's kind of the direction that we want to go, is a discrete reverse Lyapunov. And I just wanted to mention that there's already progress, there's already nice results about a discrete Procopaliner. So I'll come back to that. I guess that's foreshadowing. And so the type of objects that we'll want to give a Lyapunov reversal for are log-concave sequences. So a log-concave sequence, just a sequence of positive numbers, could be finite, could be infinite. We do require that the non-zero entries of our sequence are an interval of numbers. You can naturally get sequences that do satisfy this positivity as the coefficients of polynomials with real zeros. This is a result that goes back to Newton, but for us, we will want, but those objects won't guarantee us an interval of support, and we need an interval of support in order to make this machinery go. For most applications, this is a very natural assumption, but I'll just mention it that it's not guaranteed from the statement here. And so this just looks like, basically just looks like what you would get with log concavity in the continuous setting, just specialized to neighbors, guys, where we have n plus 1, and n minus 1. This looks just like log concavity. And I'm going to claim that log-concave sequences are interesting and come up in natural places. In probability theory, if we look at sequences that come about as the probability that some random variable, some integer valued random variable takes a particular value, then the Bernoulli, the Poisson, and the geometric all give examples of log-concave sequences with their density functions. And then an important fact is that if we have two independent log-concave random variables, then their convolution, their independent sum is log-concave. As well, log-concave sequences arise naturally in convex geometry. The Alexandrov-Fenchel inequalities imply that the intrinsic volumes associated to a convex body form a log-concave sequence. These are the Vj right here. In fact, there'll be something stronger than log-concave, but I don't want to, which is a topic that I love to talk about. Objects that are log-concave with respect to some other reference measure, being log-concave with respect to Poisson is called ultra-log-concave, and some circles being log-concave with respect to a binomial distribution is referred to as ultra-log-concave of order m. in the continuous setting being log concave with respect to Gaussian. It gives us the class of so-called strongly log concave measures in the continuous setting. But without going into that, these are all going to be stronger conditions than what we'll investigate in the following. And in combinatorics, the resolution, so this is due to the Alexandrov-Fenchel inequalities. And in combinatorics, the resolution of the Mason conjecture or Mason conjectures ensures that if we have a matroid and we look at the independent sets of a particular cardinality n and we count them and we write this number down as xn, then we can form a sequence here. And this is, I should cite some folks who this is relatively recent, this is in the last 5 years. So I should remember these names, but I don't in this particular moment. But regardless, then xn is a log concave sequence. And so what I'm advocating for and what I'm saying is interesting and useful to do is to approach these objects abstractly. And I'm citing, there's a really nice paper, relatively recent of Chan and Pak. This is called log-concave poset inequalities, where you can see how just applying log concavity and not using any ideas about matroids or and matroids, you know, you can recover all kinds of cool results in graph theory just by talking about log concavity of sequences. And then to advertise my own investigations, there's a nice paper of Lotz, McCoy, Nordin, Bacati, and Trott, building on another list of names. There's a paper called Living on the Edge, which showed that phase transitions in signal recovery type problems were dictated by the concentration of intrinsic volume, the conic intrinsic volumes, and doing all kinds of interesting maneuvering. In this paper, Lotz, McCoy, Nordin, Bacati, and Trott were able to give bounds for the intrinsic volume random variable. And again, if we scroll up just a little bit, when we're looking at intrinsic volumes, if we have a convex body in n-dimensional space, we obtain some finite sequence of their intrinsic volumes. And they were able to prove that these volumes concentrate in a Gaussian manner around their mean. And which is a really cool result. But in the investigations, you know, if you've grown up around log concavity and you want log concavity to be able to prove things like I have, we're tempted to, my friend Arnaud and his student Aravinda investigated the concentration of ultra log concave variables. And if you just approach a random variable x that is ultra log concave and supported on 0 to n, we could derive the following. Just using simple techniques with moment generating functions, we can derive a bound like this that improves the variance bound and the concentration bound. And then, of course, we're using big machinery because we're using Alexandrov-Fenchel that implies that every intrinsic volume random variable is in fact ultra log concave. And so we'll go a step further in our log concavity investigations. And talk about the conjecture. So, and again, this is just kind of for fun. So the reason that I got interested in this, in the conjecture that I'll state in just a moment, well, maybe let me jump ahead. So the conjecture is going to be the following. Let me put a box around this guy. The conjecture is just going to be a discrete analog of the Lyapunov reversal from the continuous setting. If we have X to be log concave and monotone, which actually ends up being pivotal, if you can believe it, then the following function will be log concave. And again, this is just looks like the, the P norm, more or less, type object here being log concave instead of log convex after we've added this auxiliary P. And then a stronger conjecture to completely mimic the continuous case would be the following, which to me, if this guy was going to be true, it seemed like there'd be no reason this guy wasn't true also. But regardless, so X concave, I'm just going to mean that the natural thing, if you remember how I wrote log concavity, concavity would just be the natural analog of that. And this would be for S greater than 0. And by concave, of course, I mean that we have an interval of support because we're looking at, I'm only investigating positive concave sequences. And so we must have compact support for the variable, otherwise we're in trouble. But very good, so that's our conjecture. And where it came out of, the reason I, just to give you a personal anecdote, since we're here together, so there's a result that goes back to Bobkov and Mataman in 2011, which I understand as a reversal of the Renyi entropy inequalities. And so the Renyi entropy goes back to Renyi in 61, but is defined as the following. The Renyi entropy of order P, and this is for P belonging to 0 to infinity. When P is not 0, 1, or infinity, is the following. And when you take the limit as P goes to 0, you recover the volume of the support. When you let P go to 1, you recover the usual Shannon entropy of a probability density. And when you let P go to infinity, you recover the sup norm, or the negative log of the sup norm. So this connects some interesting quantifications of randomness. We're connecting, oh, this guy needs a log right here. This is the logarithm of the support. There's no way to, right? We're not going to get rid of the log there. He should be sitting pretty. So very good. But the nice thing here is we connect in three interesting objects, 3 interesting quantifications of randomness. We connect the volume and object from geometry. We connect the usual Shannon entropy, our kind of canonical quantification of randomness, and we connect the maximum of the density, which connects us to concentration type results and small ball type inequalities from probability. And so if this is your first time seeing the Renyi entropy, and then we've had different histories, but if you're attending a probability and analysis seminar and you're just seeing the Renyi entropy for the first time, you're undoubtedly probably better at understanding P norms than me. But Renyi entropy, if you're good at P norms, you're in business, right? Because you're just taking a P norm of some variable that happens to be an L1, right? And so this is not so romantic to you. It's old hat. But just like just like anything you can do with p-norms, that's anything you can do with p-norms tells you about something you can do with Renyi entropy. And vice versa, if you're in L1, then Renyi entropy maybe can tell you something about maybe there's some exchange, maybe there's some reciprocity, I don't know. But regardless, I'm just going to be stealing analysis right here. Holder's inequality is going to show you, or Lyapunov's inequality is going to show you that the Renyi entropy of a fixed variable, a fixed density, is going to decrease with the parameter. And this is why in some literature, the infinity Renyi entropy gets referred to as the min entropy, and sometimes the zero entropy gets referred to as the max entropy. And so the result of Bobkov and Mataman was the following, is that when P and Q were smaller, when P is smaller than Q, if F is log concave, then we have a reversal. And the worst case setting is given by F of X, worst case. So you can grab the constant if you're interested, is e to the negative sum xi on the positive orthant is our worst case setting. And more personal anecdotes. Bobkov was my PhD advisor, and Makshay Mataman was my postdoc advisor. So I'm inextricably bound. I'm stuck with. I have to like this stuff. I've been conditioned, brainwashed to love it, and I do. So, and the way that this first came up to me is that I was working on a problem with Makshay Mataman, and we had this problem, and we were like, I was like, oh, it was in the discrete setting. We were looking at sums of uniform, we're doing some stuff. And I was like, oh, man, let's just use your reversal, use the reversal, and we're good. Use the reversal for its log concave, right? We're good, do the thing. And he was like, James, this is discrete. I don't have a result like that. And I was like, shoot, for real. So I started trying to prove it back when I was a postdoc, and I didn't get anywhere at the time. And I left it aside for a while until I went to visit Tomasz in probably 2019, because Tomasz and I saw each other in person. So it had to be before the pandemic. And what we were able to derive a nice result that I thought was cool. It showed that an analog, we were only able to handle the infinity case of the Renyi entropy, so fixing a maximum of our density, when X is log concave. And we actually, if you're keeping score at home, we don't need, without equality is not reached, but it can be in the limit for geometric distributions with parameter going to 0. And a cool observation that Tomasz made was, well, we're doing we did some song and dance and some tricks, but a cool observation that Tomasz made was we could get this result that I wanted if we just proved this discrete Lyapunov's inequality. We didn't have any way of getting there, but it seemed like a really elegant way to get an inequality that we wanted, was to just, prove that this is log concave. And we started checking around, and we found out, kind of surprisingly, that log concavity would fail for a log concave sequence. For instance, if you took a symmetric geometric, here I'm defining n on all of the integers, but that this result was not true. And so maybe thanks to some numerical simulations or brave intuition, we restricted the case to the situation that X was monotone. It was decreasing or increasing. And if it's increasing, it's finite. And again, I'm probably assuming that everything is in L1 here. So this doesn't rule out anything too interesting. This is just things that would increase exponentially as n grew. And so this is our statement of our conjecture. Okay, very good. And I'm happy to say that we were able to confirm it in the case that the first conjecture we were able to confirm when our sequence is log concave and monotone. The second conjecture I thought was definitely going to be true. The only reason I stumbled into it into a counterexample is because I was trying to prove it. I felt like the machinery that we had built for this setting should work over here. I just needed, and I had everything broken down, and if I could just prove it for affine functions, I would be good. And then I was like, oh, I've almost got it. If I could just prove it for like a Bernoulli, I would have it. And I spent a day trying to prove it for a Bernoulli before I was like, well, maybe I should check. Conjecture B fails for a Bernoulli. And this is with well, I don't have things normalized as probability distributions, but that's a little consequence. And so if you let lambda be small, and this seems to be kind of the problem in general with trying to bring continuous theory to the discrete setting, is that, and I don't have a better explanation for it than things kind of go wrong when objects become very discrete. And in this case, if I let lambda go to 0, then lambda goes to 0. This guy turns into 2/3 less than 1, and the thing fails. So as I let lambda go to 0, as I let the distribution concentrate at a single point, the conjecture fails. And this is not the only place that I've run into this mischief of discrete stuff being, discrete stuff is different than continuous stuff when you are especially discrete, right? You focus you concentrate the variable at a particular place. So that's our statement. See, do we usually end at 50, Tomasz? Perfect. Okay. Well, I may not go into too much detail, but when other people are talking, I can never follow the details anyway. So it seems unfair to subject an audience to the same. So the outline of the proof is really a simple ideas, essentially. So the function that we were looking at, this phi for a fixed x, and I write a subscript x sometimes if I want to remember which sequence I'm talking about, has two symmetries. I can scale a log-concave sequence by a constant, and it will remain a log-concave sequence. I can also raise it to an exponent, and it will remain a log-concave sequence. Just playing with those two symmetries is going to show that it is enough to prove the result when x, if it's in L1, right? We don't want to talk about it if it's not. X is a probability density, and we can scale things around so that we're only talking about concavity at 1, or yeah, the log concavity at the point 1. And so that simplifies things a little bit. Log concavity at the point 1, where p is larger than 1, just by playing and scaling things around. Then if it's a probability density, this guy goes away. And the only thing we're looking at is I need to prove this guy is bigger than this guy. That's step 1. Step 2, once we're in a setting that I like, I'm more comfortable talking about probabilities, then we identify the worst case scenario. And me and Tomasz already had, with Tomasz's help, we had a good idea of an extremizer, right? Because the geometric, we had already proven extremized things in the infinity case. So the next thing to do is to prove that that if you fix, excuse me, this should not be a P. This has got to be, or oh, it's not a P. If you match the P norms, then the minimal Q norm. So you fix a probability density, you fix the P norm, then you minimize the Q norm among log-concave monotone variables, then the geometric remain an extremizer. And then the third step is just completely computational, no problem at all. You just, in the special case that Z is geometric, you just prove it's log-concave. And the way that we did it was we just took a second derivative. We didn't do anything clever. We just believed. I did the computations, and it's easy to show it's less than 0. And so once you have this in hand, if you believe my reductions, then if I want to prove phi x is log-concave, you just observe that this guy, the average of 1 and a P that's bigger than it, is going to be a Q, where Q is, this is for Q in between P and 1, then this is my Q. I use the result to compare to a geometric. I have the result for a geometric, and the geometric has the same P norm as X. Boom, did nothing. So there must be some content to the theorem, right? This is just playing with algebra. This guy's just playing with calculus. And so item 2 is where the content lives. So going to the proof of 2, the idea is just uses classical type tools, is to look at the distribution functions, right? If I look at, for a particular sequence X, if I count, I have my sequence, and then I draw a lambda. If I just count the number of guys that are above the line in my sequence, Fubini-Tonelli is going to give me that my pth power, the sum of my pth powers of my xn's, can be described in terms of a continuous integral. And now I'm in business, because continuous stuff is nice to work with. And so if I write x tilde, we've already been able to normalize so that the sum of the xn's when p is equal to 1 is 1, when we say we're a probability density, and that's going to say that f of x right here, this guy, this will integrate to 1, right? When p is equal to 1, that goes away, it integrates, this guy goes away, it integrates to 1. And so I define a probability, a random variable. I have a probability distribution. I define a random variable, x tilde. And then when z, remember this is when z is geometric. Oh, my apologies, guys. I feel like red is too serious of a color to use so frequently. I don't want you to feel like you're looking at my homework. So z is a geometric distribution. I define z tilde to be its distribution function here. And if we look at the assumptions that we have and the thing that we're trying to prove, if we're matching the p norms of these sequences, then we're matching the p-1 norms of the random variables. And what I'm trying to prove then is that the expectation of the moment of this auxiliary random variable is minimized by the geometrics auxiliary random variable. Ooh, let's not do that. Very good. And so now that we're back happily in the regime of random variables, the trick that we use, oh my goodness, is a classical result. I think this probably is due to like Carlin and friends in like the 60s or something like that. But I've also seen it. It's also in the economics literature where they study different types of stochastic orders. And the result is if you match, if I have two random variables and I match expectations, and then if I say that there's some interval, let's draw a picture. There's some interval where f of v is bigger than, here's f of u. If there's some interval where this guy is bigger than the other guy, then if I put a convex function, the statement in terms of majorization is just in the convex order that that U majorizes V. And this is going to make sense because if you have a convex function, convex functions are going to grow at the edges. I'm talking out loud to make sure that I wrote this correctly. Convex functions are going to be big at the edges, and if I have more mass, we match the means, the intuition here. My mean sits somewhere in here, and this guy is going to have more mass out at the edges, right? Because on the interval, the green guy is bigger, the blue guy is bigger on the edges. Convex functions grow out to the edges, and so I should have that the convex function composed with U is bigger than the convex function composed with V. Maybe due to Carlin. And I'll say et al. And this can be easily extended to the case where you match Pith moments, right? Because the punchline here is that if I match Pith moments, I can write the density of the Pith moment. If U and V's densities cross twice, then if I have some strictly increasing function, they're going to cross. You can describe exactly where those two things happen, and we have the same sort of result. So if the original densities cross twice, then the Pith powers are going to, the densities of the Pith powers are going to have to cross twice. And so the crux of the matter is just proving that f of x, these auxiliary density functions, cross twice. And basically the reason it's going to happen is because one guy is log affine and the other guy is log concave. And so if you look at their potentials, or well, I guess I'm looking at the negative of their potentials, they're going to look more or less like that from a distance. A disclaimer is that this fact is false without monotonicity. It's easy to make a counterexample if you try to. It's not true without monotonicity. And this is due to the jumps that you encounter in the discrete setting. In the continuous setting, it's an interesting direction, I think, and you can actually work things out, and you can recover the results of Borel and some that have followed since then with a similar approach. But in the discrete setting, the monotonicity is crucial here because they won't necessarily cross twice. We need monotonicity here. And so to apply this to our sequences, we can write our x tilde to the q minus 1 as a concave function composed with x tilde to the p minus 1, right? I take this particular function, and then a concave function is the negative of a convex function. This is going to flip the orders around right here. And boom, we get our inequality. And that gives us our minimization and concludes the proof. Just super fast, I'll just mention the applications that we get. We're able to get a nice Renyi entropy comparison, a discrete analog of, well, my pen's tired. You guys probably are too, but we get a discrete analog of the Bobkov-Matamon type Renyi entropy comparison. We get sharp var-entropy bounds, if you're familiar with var-entropy bounds, for log-concave monotone sequences. And we also get this cool, I think of it as an analog of there's a theorem of de Roche that says that the mode of a sum of independent Bernoulli variables, not necessarily identical, but independent Bernoullis that the mode and the mean are within one of one another, which is a fantastic result. This is not true. And this is being the sum of binomial Bernoullis is much stronger actually than just being log-concave. And such a result fails in general for log concavity. But what we have right here is a result that says that if we evaluate at our value at the mean is a quantitative result, that our value at the mean is, well, of course, it's going to be less than the max of the density, but it's within a factor at the expectation. And lastly, we're able to sharpen up this, what I'm calling a discrete entropy power reversal for the sum of IID log-concave monotone variables. We get a sharp comparison of their sum. And I'm already 2 minutes over, so thank you guys for your patience. If it's any consolation, I have further artwork and calligraphy.
Let's virtually thank James for the talk. And I would like to ask if anybody has any questions at this point. Just please go ahead and unmute yourself or use the chat if that's more convenient.
So this may be a little bit off topic, but I have a question about something you wrote way back at the beginning.
Sure. Hey, Joe. Good to see you.
Hey, how's it going? Yeah, thanks for the talk.
Pleasure. Thanks for coming.
So you had this, you mentioned this result by Nordin to Picati and so on about concentration of intrinsic volumes.
Yes.
And then you had an improvement over it when you...
Shameless advertising. Let's hope it's correct. I think it's towards the, no, let me go. Log-concave sequences. There we go, right here.
Yeah. So I was curious because so in the second line, you have, okay, the variance is bounded by the expectation, which is always better than for n because it's between 0 and n, right?
Yes.
But the exponent, the Gaussian concentration you get is of order n and not of order the expectation. Does that make sense?
Say that again.
So on the left-hand side, you show that it's concentrated, right? Is that like, is there something going on there? Like, could it be that you have log-concave sequences with much smaller expectations that are much smaller than n? But
yes,
like,
yeah. No, and this, well, no, I think I understand the question. So we have one result that's in terms of expectation, and so we have something about the variance, but then this over here is in terms of n.
Right.
And if I'm being honest, I don't understand it completely.
Okay. So it could be true potentially that you could put the standard deviation instead of n.
Right. And this is, yes, exactly. And so I can tell you where the result comes from. And basically what we proved at the time, we proved the following, that if you took something that was ultra log concave, we proved that if I match the first moment with Z being Poisson, then the moment generating function of the Poisson dominates the moment generating function of the ultra log concave variable. And so essentially, once we had that in hand, all that we did is we robbed the literature because the Poisson concentration bounds are really well known. And I mean, and then once we had that, I mean, we've got this paper with a bunch of awesome mathematicians on it. And so we wanted to be like, hey, you know, like we're doing good stuff too, which related to these heavy, awesome guys. But the question that you bring up is perfect because, right, we said we'd like, what would be even cooler is to put the standard deviation there. And that I have no reason, right? I have no reason to say it's not so. Just that we didn't get that. We just got so pumped that that this thing came together that we wanted to send it off. But yeah,
Cool.
yeah. Thank you for the question.